Today we are going to learn some important formula in chapter 2. This formula involves the calculation in chapter 2. So the first one actually is this one. When the electron at a stationary state, okay, we are apply this formula, negative RH1 over n square. Okay, n is the principal quantum number. It started from 1 until infinity, and then the variable constant is with this value. This is used to calculate the energy of an electron at stated energy level. Okay, another one is this one. The second one, suppose this one, the difference of energy. Okay, used to calculate the energy during the transition of an electron. So the unit is in joule or kilojoule. Okay, if energy released, so that value of the energy is negative. If the energy absorbed, and then the value of the energy is positive. But normally in your syllabus, right, okay, when an electron, normally the electron is moved from a higher energy level to a lower energy level. So it is in negative value. Beside that, there is another formula to calculate the delta E, so which is H mu. H is Planck constant with this value, and then mu is referred to frequency. So based on this formula, right, we need notice that energy actually is directly proportional to frequency. Again, it's delta E, so the unit is in joule. Okay, next is lambda. Lambda equal to C over mu. Based on here, right, okay, we notice that mu is equal to C over lambda. If we substitute over this formula, we will get delta E. Actually, also can apply the formula Hc over lambda. Okay. So in this case, if we apply this formula, C is a constant speed of light. The value is 3 times 10 to the power of 8 meter per second. Okay. And then, based on here, you know that lambda actually is inversely proportional to frequency. Lambda means wavelength. Okay, the unit must in meter. And then frequency, the unit is in hertz or per second. Okay. Another formula which is 1 over lambda. There's a name for 1 over lambda which is wave number. The unit is per meter. So RH1 over n1 square minus n2 square. Always remember the n1 must smaller than n2 because lambda value always positive because lambda is referred to distance. So the unit for lambda is meter. Okay, in this case you have to take note. The Rybert constant for lambda is 1.097 times 10 to the power of 7 per meter. It's different with the lambda in calculating energy. So the possibility, the question will ask you to find out the wave number, find out the lambda, or find out the n value. So let's try some example. So the first one, calculate the energy in joule of an electron. Okay, occupy, so n equal to 3 and n equal to 4, meaning that this is at certain state. So we are going to apply En. And B, the E of a photon emitted 1 mole electron of drop from the fourth energy level to the third energy level. Let's check the solution. So for electron at n equal to 3, so formula, substitution, find the answer with unit. So negative is referred to energy release. Okay, and then energy of an electron at n equal to 4, so formula, substitution, find the answer with unit. So this is the final answer. Okay, for part B, the energy of the photon emitted when 1 mole of electron of drop from the fourth energy level to the third energy level. So we are applying the E final minus E initial to find the difference of the energy. So the E3 and E4 we already calculated in part A, so we just substitute and then we get the answer, negative 1.06 times 10 to the power of negative 19 joule. So this is the energy released by one electron. But the question 1 mole of electron. So that's why I need to times the number of Avogadro in order to get the 1 mole of electron release energy. Okay, The negative sign indicate energy is released. Okay, example 2. This question, okay, also calculate the energy released when an electron from the 5th energy level fall to the 2nd energy level. So initial is 5 and then final is 2. So formula substitution, final answer with unit. So the negative sign actually is refer to energy release. If you make the conclusion energy release, right, the release already represent the negative sign, so you no need to write down the negative sign. Okay, next. Okay, this question calculate the wavelength in nanometer. Okay, and then given energy, okay, electron drop from the energy level equal to 5 to the energy level to n equal to 3. In formula to calculate the E first, delta E, formula, substitution, final answer with unit, so the energy release is negative 1.55 times 10 to the power negative 19 joule. Okay, next, the second formula that you are going to apply is delta E equal to Hc over lambda, because the question want to find wavelength. So lambda equal to Hc over delta E. Okay, Hc over delta E. Okay, H and C is the constant which you can find from list constant, and then delta E you just find from here. Okay, the question want lambda. Lambda means a distance in meter. That's why this you can ignore the negative sign that you found that you calculated at the early part. So just ignore the negative sign. Okay, Planck constant, speed of light constant, joule cancel, second per second cancel, so the final answer, the unit is meter. Okay, and then the question want us in nanometer. That's why you must know how to convert to nanometer. Next, the question is calculate what is wavelength. Okay, means lambda, frequency mu, and then wave number means 1 over lambda. The last line of hydrogen spectrum in Lyman series. Lyman series actually is n equal to 1. The last line of hydrogen spectrum is referred to n equal to infinity. So before you answer the question, you must get the idea. Last line is referred to n equal to infinity. Lyman is n equal to 1. Formula, substitution, final answer with correct unit. So lambda is in meter. So we continue with frequency. Okay, C is the light constant, speed of light constant, and then lambda that you satisfy in part 1. So just substitute, and then final answer with correct unit. Frequency is in hertz or per second. 1 over lambda is referred to wave number. So again, you just substitute the Rydberg constant. Okay, this is lambda, so this is the Rydberg constant for lambda. And then substitute the value, and then you get the answer 1.097 times 10 to the power of 7 per meter. So the unit for wave number is per meter, for lambda is meter. So the different value of Rydberg constant and usage, if for lambda, okay, is 1.097 times 10 to the power of 7 per meter. Okay, if for energy is 2.18 times 10 to the power of negative 18 joule. So that's all for today. Don't forget to follow my IG at ChemiComSL. Subscribe, like and share my YouTube channel ChemiComSL, and follow my Facebook ChemiComShirley. Hope you all learned something. Thank you.